Hello everybody and welcome along to yet another webinar with photothermal spectroscopy. Today I'm thrilled to be joined by Angelina Lau. Angelina is a principal engineer and lead in the product yield enhancement team at Micron Technologies. She's based in Singapore. And today she will be my guest speaker in the second half of this webinar. The overall theme and title of this webinar is Identifying Organic Contaminants with Submicron Infrared and Simultaneous Raman with Fluorescence Imaging. Myself, yours truly here is Mustafa Candace. I'm the Director of Product Management in photothermal spectroscopy, and I've been doing infrared and Raman in various shapes and forms for probably a good quarter of a century now. And it's always really exciting to be talking about cutting edge of technology. A couple of housekeeping rules, I suppose. As always, you are welcome and encouraged, in fact, to type in your questions into the chat box there. All of those questions will be attempted, at least, to be answered at the end of it, assuming we have some time left. I hope we do. Any questions we fail to get to, of course, we'll get back to you via email in the subsequent days. And really, without any further ado, I want to jump into it because there's a lot of cool stuff that Angelina will be showing in the second half. So the outliner today, I'll start off with some pros and cons and just a general sort of, I suppose, landscape of infrared and Raman microscopy, and even some other commonly used failure analysis techniques. I'll then introduce to you how OPTIR works, some of its new options, some of its new features, and how it overcomes a lot of those challenges in that first section there. I'll then take you through a number of industrial failure analysis applications. Before I hand over to Angelina in the second half. And she can then talk you through two interesting case studies or examples that she's used this tool for in her line of work at Micron Technologies. So in terms of infrared microscopy limitation or infrared spectrum microscopy limitations, being a technique that uses long wavelengths, inherently long wavelengths mean lower spatial resolution. So if you're dealing with wavelengths in the mid-infrared that are anywhere from sort of 3 to 15 microns, your resolution is going to be limited to that sort of ballpark. There's often complex sample preparation. So if you want to measure things in transmission mode, which gives you generally a better spectral quality, you've got to cut them thin, and not everything, especially in an industrial sense, is amenable to be cut thin or maybe even polished or cut to a flat surface. Some of those are overcome or mitigated to some extent by using ATR, attenuated total reflectance, and that's a contact technique. So rather than using light, infrared light, you actually direct the light through a germanium or diamond crystal and then touch your sample. But of course, touching means contact. It means risk of contamination, means risk of damage to the sample and or the crystal, which can be quite expensive to replace. And any time you touch something, you leave an imprint. And here's an example there of the imprint of an ATR tip along the surface of a sample as multiple contact points have been made. So, of course, ideally, you want to avoid that. One perhaps underappreciated, complicating issue with traditional IR microscopy, or FTIRs or QCLs, is the potential for dispersive scattering artifacts. So in an ideal world, as I said before, in a thin transmission measurement of a thin polymer, in this case, as drawn here, as schematically, infrared light transmission measurement, you get a nice spectrum. That's a nice flat baseline, symmetric peak shape, all looks good. But if you take the exact same material and measure that in transmission mode, in a not a flat thin format but a spherical bead of say 15 microns, the little spectrum looks very different. And if you change the size of that particle, keeping the chemistry the same, the spectra changes. So it really goes to show how spectra are not just always, at least in traditional systems, are not just always reflective of the chemistry, but there's a lot of sample morphology and topology that is convoluted into the spectral shape, which of course means identification and interpreting the spectra can become difficult and can sort of mislead you. That was infrared. Raman, of course, has been around for a long, long time, and Raman's strength is its spatial resolution, which is why so many people use it, but it's Achilles' heel, and I'm sure anybody here who has used Raman microscopy will shake your heads knowing that autofluorescence is a major issue and an impediment in many cases. For biologicals or even biological contaminations in industrial settings, skin flakes and so on, can often have significant autofluorescence, which can swamp the signal. You can go to longer wavelengths, and that helps a little bit with, though not completely, with fluorescence, but that you take a massive hit in sensitivity. And that's on top of already a limited and poor sensitivity, fundamentally, with Raman. For anything imaging, you need to collect hyperspectral images, so point-by-point mapping, which is a very slow exercise. And to overcome some of those limitations, those sensitivity challenges, you often have to pump in a lot of laser power. And you often find that you're running a fine balance between too much laser power, which burns and damages your sample, or too little laser power, in case you have not enough sensitivity. And then sometimes there's, if you're using different lasers, you have different spectra turning up, and it could be because of the substrate, it could be because of resonances in your sample, and so forth. Right? But they were supposed two examples of vibrational techniques. Other common analytical techniques in an industrial failure analysis setting might be optical microscopy, and that's great, it's cheap, it's ubiquitous, easy to use, but it only provides you morphology, shape, maybe some color. There's absolutely no chemical info in that. And in reasonable spatial resolution, you might get sort of in the few hundreds of microns, few hundreds of nanometers and up to a micron or so. And maybe the workhorse in a lot of industrial FA setting or laboratories is SEM, scanning electron microscopy. Now, that is quite expensive, though it does give you exquisite spatial resolution. It has, in a SEM-only setting, it has low chemical specificity. In fact, there is none. If you add EDX to it, you get then elemental information, but again, that's limited information. It only gives you part of the picture. To really resolve the full puzzle of what this particle is, where it's come from, how do I get rid of it, you really need molecular information, and that's really what it lacks. And that's really why the tool that we're about to talk to you in this webinar has found such great utility and great excitement in this setting. And really with that, I want to introduce to you here optical photothermal infrared, so OPTIR. So what is it? It's basically a pump probe technique. So there's a pump, it's two lasers, two beams. The first laser is an infrared laser that we use to pump and excite the sample. That's really where the infrared spectroscopy comes from. And then we use a secondary probe beam, a short wavelength laser, typically green or near IR, to detect the result of that excitation. Right? And because we use this probe beam, the very short wavelengths, we end up with Raman-like spatial resolution, but we get all of the richness of infrared spectroscopy and what benefits of it. We work primarily in reflection mode, which is that easy-to-use mode. It's point and shoot. But unlike regular FTIR, where reflection mode, you end up with all sorts of distortions, reflection mode with OPTIR, you end up with spectra that look just like regular FTIR spectra that have been collected in transmission or ATR mode. It's non-contact, it's far field, and the spatial resolution is wavelength independent.
How might this technique work? I've got a little video to take you through it. So it all starts with the microscope objective. It's a reflective Cassegrain style. Through that, we shine a pulsed infrared laser beam, and being infrared, it's fairly broad, maybe around 10 microns. At the same time, we're shining in our probe beam, the green, it's about 500 nanometers. The infrared generates thermal expansion as it's expanding, and that thermal expansion changes the way the green light is reflected or scattered back. Right, so as we're tuning our infrared laser from one wavelength to the other, we monitor the intensity of the green light reflected back. And it's from that we calculate out what is essentially a pure infrared spectrum collected in reflection mode.
So in terms of OPTIR measurement modes, it's a pretty three modes of relevance to this sort of application setting. If that blue box there represents your field of view or your measurement field of view as seen on the software camera view, you can simply point and shoot and click a few points and say, hey, give me some infrared spectrum Raman from here. And that point and the measurement spot size there will be about 500 nanometers in diameter. Right, you could work in array mode. where you can perhaps do an array of points across an interface and look at the chemistry as it evolves and changes on either side of that interface. If you want to do some mapping, hyperspectral imaging, in a traditional mapping modality, you can do point-by-point imaging. I call it more of a discovery mode, perhaps where you don't know what's in there. You may need to collect everything. So you get a full three-dimensional hypercube of information. And perhaps one of the more interesting modalities that are really made possible through the use of these emerging QCLs is single frequency imaging. So if you know what you're looking for, rather than collecting every single wave number across your spectrum, you can do selected or targeted chemical imaging where only certain frequencies are collected, certain wave numbers, images, and that speeds up the measurement dramatically. Right. Another really exciting element of what we do and why this has just generated so much excitement and uptake in the industrial failure analysis community is the fact that we now bring these two techniques together, these being infrared and Raman. So infrared and Raman has always been complementary, but they've been done on very separate platforms. So now really for the first time, you've got them on the one tool, on the one measurement. So it's same spot, same submicron resolution at the same time. And this is a world first and still a world first. And I'd like to take people through this sort of simplified schematic of the instrument, because I really find that it helps appreciate how it's done and how exciting this is. So let me take you through this. So this is our quantum cascade laser, so that's where it all starts. The infrared laser is shone through a number of optics, focused through a reflective Cassegrain kind of FTIR style objective. That focuses the infrared beam as sharply as or tightly as it can. That probe beam, as I've explained before, is collinearly introduced, the green beam as depicted in this image, and that's focused down, and that's where that photothermal magic happens. The reflected green beam goes back to a visible detector, and I need to stress that because there are no infrared detectors, there are no liquid nitrogen or other cryogenic cooling required here. It's all room temperature visible detectors, which make the optics much easier and much more sensitive. So that visible detector extracts out the modulated infrared components in there, but because we are using a Raman grade green laser, you've got Raman scattering happening all the time. You know, whether we like it or not, whether we even use those Raman scattered photons or not, they are there. So we take advantage of the fact that there are wavelength shifted Raman photons. We use a dichroic optic here to filter out or separate out only the Raman shifted photons and send those over to a Raman spectrometer for Raman signal generation. Right? So really in doing so, it's very efficiently and effectively, dare I say, elegantly, we separate out only the Raman and send it off, and all the other light is used to generate and extract out the infrared signal. So, and thus we end up with that true complementarity, because the infrared and the Raman come from the same spot at the same time with the same resolution. Right? The pump source, and that's a quick, I'll spend one slide on that because I think it's really important. That's where it all starts, of course. The standard QCL that we offer covers the bulk of the fingerprint, so that's about 1800 to about 970. There are high wave number OPO options, that's separate dedicated lasers, but much more commonly, and my personal favorite is the addition of a CH region chip onto your QCL. So with the one device, you can cover your fingerprint region with the main and quite important and distinctive CH bands. But there are also these new tri-range QCLs that also cover this so-called silent region, where not much absorbs, but there are a few quite characteristic bands. So if you're likely to encounter things like nitriles, alkynes, and maybe some deuterated components and thiocyanates and other things with sort of triple bonds, then that might be a really interesting option for you to consider. But otherwise, I think that most of our systems are probably sold with a CH fingerprint QCL, or if you want to go as low as possible, you can go down with a wide range to about 800. On the probe, which of course doubles as a Raman excitation, you've got the 532 as standard or the 785, and that's optional. And that can be quite a useful one in an industrial setting, because green can often result in easy burning of samples, because green, anything black, anything reddish will just absorb the green, and very quickly things heat up. So 785 can be a really useful option for minimizing those effects, but I'll talk about other means to minimize that effect as well. One one of many sort of things we are proud about is the spatial resolution breakthrough. So as I said earlier on, traditional FTIR and QCL microscopes really lack resolution, which has really impeded their adoption and full utilization. But the fact that, and let me explain to you how and why that's the case, at least with those, because remember, if they're using very broad and long wavelengths, this equation here, this Rayleigh criterion, is a very simplified approximation for spatial resolution. So if that lambda value there ends up being quite large, sort of 10 microns and so on, as is used in the mid-infrared, and if we plot that, we can see that in the fingerprint region, which I've grayed out here, spatial theoretical resolution is kind of up to about 10, more practically probably in the low to mid-teens. And that limits the small things you can see and determine and characterize. Of course, with the probe on the OPTI Mirage microscope being 532 nanometers, so 0.532 microns, with a high NA objective, theoretically, that's now in the low 400s, and that's flat across the full spectrum as well, right? So it's not wavelength dependent, much like Raman. Right? And really, that's where the 30x improvement that we claim comes from. In terms of, and that's kind of it for the introductory aspect of it. I'm going to move over to walking you through a number of applications. And whilst we do a lot in life sciences, there are also loads of applications on the material science side and industrial sides, ranging from cultural heritage, failure analysis, of course, what we'll be talking about here, but even really cool examples of paleontology and polymers and forensics, and really the list goes. And I'd certainly encourage anybody to jump on our website, or even just jump on Google Scholar and type in OPTIR and enjoy the list that pops up. But today we're really talking about semiconductor or high-tech failure analysis. And I'll take you through an overview of the platform and its sort of three versions and how each version benefits and the characteristics that it has. Right? So I'll take you through initially the Mirage platform. The Mirage is an IR-only sort of base entry-level submicron system, and that's great for just general material characterization, contamination analysis. If your sample is likely to have carbon-containing components, of course, that's where Raman shines. So that's really where the true complementarity is exploited, because now you're taking, what Raman is really good for is maybe aromatics or dark or carbon-containing components. So then with the addition of Raman, you've got those bases covered as well, and that's the Mirage R platform. And then really the top-tier platform at the moment is the Mirage LS. And that kind of does all of what these do. So it does all the infrared, does all of your Raman, simultaneous Raman, but now we've added fluorescence. And that is a really cool option, which I'll talk to you about in the coming slides. So with the more base Mirage microscope with its submicron IR capabilities, it works primarily in reflection mode. Remember, that's also really important because you don't want to do transmission. You don't want to be touching things, so you don't want to be making contact with an ATR tip on that at all. And you can get spectra from almost basically any substrate, whether it's glass, plastic, metal, all the things, or deep in the cavity, and I'll give you some examples of those as well in the coming slides, all the things that you just cannot do with a regular FTIR microscope, or even Raman for that matter. Another classic example is foreign matter between solder bumps. And the challenge for regular vibrational spectroscopy here is that these are recessed, right? You can't actually get to them. So reflection FTIR just doesn't really work at all, generally speaking. And ATR cannot reach into these recesses, right? And so here we've measured, so this foreign matter is on the order of 60 to maybe 120 microns in size. So it's actually relatively large, but the challenge, of course, here is the fact, as I said there, is that it is recessed, right? But being a far field optical technique, we can just direct the beams of light directly onto that foreign matter particle. And these are the sorts of quality spectra we get. These are only collected in a few scans. So that's maybe a few seconds, 5-10 seconds tops. And then we run these through a library match. And of course, this comes back as some sort of maybe biological matter, maybe some skin flake, and so on, right? And so those sorts of foreign matter particles are also traditionally very difficult to measure with Raman because they often fluoresce and they burn very easy. Here we've got a demixing tape residue on glass substrate. So to be able to collect organic chemical information off a glass surface would really not be possible with traditional FTIR because glass isn't particularly reflective. And the glass, where it is reflective, there are some absorbances which generate some weird artifacts. But over here, what we see are some regular looking organic peaks. Now, there is a broad sort of peak there as well. That's the silicate from the glass. So superimposed on the glass chemistry, because we are measuring chemistry, whether it's on the glass itself or the glass itself, or on the glass or the glass itself, there's still chemistry there. So we really are detecting the entire chemistry. But quite nicely, we see just from the spectra alone that there is some chemical heterogeneity. We take a few of these peaks and we do single frequency imaging with those, and then if you overlay them, you can very quickly see where these particles are. And, we've also measured these with the built-in ruler tool, and some of these are 2.5 microns, 1.5 microns. These are all in the infrared and done in reflection mode. Right? So really, with no contact, we've been able to characterize some of these adhesive residues, right? And really without any, in a very much non-destructive manner as well. This example comes from a hard disk manufacturer. In fact, we have published some papers on this in the past. And what I like about this example is that, if it's hard to, maybe hopefully you can see in some of these darker spots, because these are the failures or the areas of interest for understanding the chemistry there. And the feedback from our customers directly themselves is they believe that they are measuring particles or films or little spots as thin as 16 nanometers, right? And they've been successfully measured, and the user's own assessment shows that up to 90% success in identification of unknown organic contaminants. Now, 16 nanometers is phenomenally thin when it comes to infrared microscopy. So a regular FTIR has absolutely no chance at seeing that. But not only spatially can we do submicron in terms of film thickness, well, it can be, and in fact, I believe in-house we've done maybe as thin as about 30 nanometers. All right. Moving on to the Mirage R, which is the same as the regular Mirage, but we've got now the addition of a Raman spectrometer. And that gives you a broader characterization, particularly for dark and carbon-containing samples. In this case, we've got this is kind of more of a mock sample. This is 3 micron beads, 3 micron PMMA beads in amongst salt crystals. Now, any regular FTIR, if you attempt to measure organic particles in the presence of highly scattering salt crystals, your spectra will look hideous. You'll get absolutely nothing out of it. But in this example, we've got good-looking Raman. We've got absolutely good-looking infrared spectra. Right? So this is collected simultaneously. And the nice aspect of simultaneous collection is that you can also then do simultaneous spectral searching using the Wiley know-it-all databases. So rather than searching the infrared and the Raman separately, you can search them simultaneously, and then it will give you a two-dimensional scatter plot. So on the y-axis, you'll have the Raman spectral hit quality index, and on the x-axis, you'll have the infrared spectral quality hit index, HQI, and of course, the upper right-hand corner, it means you have a good IR. So each one of these dots represents a pair of infrared and Raman reference spectra, and unknown as well. So the upper right-hand quadrant means that, that red dot there means you have a good infrared match and you have a good Raman match. And that's exactly what you want to see to have that confidence that, I do have the right identification. Now, if it turned out that the IR was good and Raman was bad, or vice versa, well, then that's maybe cause for you to go in and dig a little deeper. Right. Over here, we're looking at, again, some dark material. So OPDR has consistent advantages when analyzing dark colored materials, typically found in microelectronic components. So in this example, we have a capacitor. It's been cross-sectioned to analyze the dielectric layer in between the metal casings and metal core. And ATR simply cannot access that. So we've operated in reflection mode, and the spectra that we generate look normal, but there is dark. So it is dark, so there is some carbon, which means an elevated baseline. And that would be the same for any IR technique. But that elevated baseline is a clue that maybe there is some broadly absorbing carbon. And then the simultaneous Raman that's also collected absolutely confirms that, because we've got these very strong D and G bands, very, very characteristic of the presence of carbon. So again, really, it's that complementarity of infrared and Raman that really work well together here. I think I hinted early on about dark samples and how different color lasers are useful, but another way to manage working with green with dark samples or even reddish samples, really, so anything that absorbs a green. So in any regular Raman system, if you have a dark or red sample and you're working with a green, the only choice you have is to lower the Raman laser power to avoid damage or burning, and sometimes you just can't avoid that at all. But when you do that, of course, you lose sensitivity. Now, the same is sort of true with us as well, with OPTIR, in that with the standard visible detector, as you lower the green power, things will get noisy. But we do have the option to switching to a low power detector. So this is an ultra-sensitive APD. It's an avalanche photodiode that only operates in the microwatts region. So you drop the laser power so low that you're no longer damaging the sample. You're still getting really good infrared spectra, as you can see in the blue there. But at those levels of low probe power, Raman no longer becomes possible. So think about in your day-to-day workflow where you may have had a dark sample or a colored sample where Raman just burnt it, and almost no matter what levels of power you used, and of course if you go too low, you lose sensitivity. So for those sorts of samples, this is absolutely works wonders. And really the third set of examples I'm going to give you here are using co-located fluorescence. So this is the Mirage LS platform. It's a different platform based on the same sort of principles, still has infrared, has Raman, but we've added fluorescent, a wide field epifluorescence module on top. And this has actually turned out, from a product development perspective, whilst initially really focused on maybe life science applications where fluorescence is quite common, it's actually turned out remarkably useful for a whole host of other applications. Industrial failure analysis is certainly one of them. And it's quite encouraging to see many of our industrial failure analysis customers buying systems with this option, or those who have purchased previously are actually adding the option to their existing system because they've seen the utility, and I'll take you through that. But really what this means is that you can now collect visible images, you can now collect fluorescence images, and I'll show you some examples, and you can use the extra contrast, extra chemical information in those fluorescence images to then guide your subsequent infrared spectroscopy chemical characterization. Right, so in this case, fluorescent imaging provides for an extra alternative layer of chemical information, sort of preceding the spectroscopic information that's not obvious in the visible. So that's an optical image. In the autofluorescence images, there are extra spots. I mean, some of them you can see already in the bright field, but some of them you can't see in the regular bright field. So there's that extra contrast that autofluorescence gives you. And then you can use either the fluorescence image or the visible image to guide your infrared spectroscopic measurement. And what this shows also is that those dark spots are quite fluorescent. So if they're fluorescent, that means Raman is ruled out. But of course, OPTIR is completely fluorescence immune. You can have the world's most fluorescent sample, and OPTIR will still work like a treat. Right, so again, it's really highlighted where those organic foreign materials are. And then with Feature Finder, which is something I'm not going to be able to get to, but it's a software tool that allows you to automatically detect where the particles are and then go back and automatically collect them. Right. Another example here, so this stop edge, it's called, may sometimes lead to micrometer-sized void that could be easily cracked in the field. And so with the co-located fluorescence, we can rapidly sort out or look for contrast in the fluorescent image that is not always clear in the optical image. Right, so spectra have been collected from these marked locations here in the optical. Unfortunately, the markers weren't carried across to the fluorescence images in this case. Right? And then we see the excellent chemical characterization. So no more do you have to scrape the underfill and then do bulk FTIR. This measures the chemistry that you need to solve these puzzles directly with minimal sample prep on the front end. Right. Another great example, so using fluorescence guided OPTIR, this foreign matter with different chemical characteristics can be highlighted directly. So in the fluorescence auto image, and the autofluorescence image, we can see that there's very something shining very brightly there. You can then guide the system to collect spectra from those points, even just in here as well. And we can see that these blue spectra have these characteristic peaks. Now, if you're familiar with biological spectra in the infrared, you can almost be certain that is some sort of biological contamination, maybe protein, skin flake, and the like. So if you do single frequency imaging at that 1660 peak, which is the strongest of those sort of protein bands, it really shows you clearly how this is all along that sort of interface between where these two components touch each other. And I think really that was the end of my application examples. I'll quickly summarize before I hand over to Angelina, but I think this fluorescence guided is a real gem because it's novel. People are really excited, and we've just seen it on a day-to-day usage how useful it is to have fluorescence in addition to your optical images. It just provides that extra contrast that optical microscopy cannot. To summarize OPTIR, again, it's submicron IR that FTI can never do. You can do dark samples, colored samples. All of those limitations of FTIR or Raman with its fluorescence are now overcome. The simultaneous IR and Raman is really cool, especially if you've got dark samples that are perhaps carbon containing, and it's completely compatible with existing preparation techniques. Right? And also, the spectra you collect are compatible with any databases you may have developed in-house with infrared or Raman, or certainly compatible with the commercial databases as well. And we'll leave the questions to the end. At this point, I'm going to hand over to Angelina. Angelina, tell us how you use it in your day-to-day life. Thank you.
Thank you, Mustafa, for your introductions. Hello, everyone. My name is Angelina Lau. I'm coming from Micron Semiconductor in Singapore. And together with my management, Peng Hui Tan and Michael Law, last year we managed to come out a case study for the topic of the OPTIR. The topic that we come out will be enhanced failure and contaminations analysis of challenging microelectronic specimens with optical photothermal infrared spectroscopy, which is OPTIR. Before I start my sharing, I would like to introduce myself. I am holding a principal engineer list in Micron Semiconductor, and I have been working in Micron Semiconductor Singapore for the past 16 years. We start to own this OPTIR in 2021, if I'm not mistaken. And this is the first OPTIR that we have in Micron. So we are glad that we managed to use 2023 whole year to really study these new techniques in Micron and try to move this technology into the Micron product. So this is the objective of my sharing today. So first, I would like to present a viable spectroscopy solution that neither the conventional FTIR nor Raman microscopy can achieve. Second, I would like to highlight the capability of submicron infrared OPTIR techniques toward unknown identification without requiring any stringent sample preparations. The last one of the objective will be, I would like to resolve the challenging aspect of analyze sub-10 micrometer, which is a very small spherical contaminant on silicon die using submicron OPTIR. So today of my talk, the outline will be, first I will do introductions. Second, I will share the first case study in Micron and another case study, successful case study in Micron. The last one will be, I make some conclusion of my today's sharing. Introductions. We all know that for conventional FTIR, there is a limitation with the resolution, poor resolution, meaning that most of the time, FTIRs, which is Fourier transform infrared spectroscopy tool, they're only able to analyze the sample with the spot size more than 25 micrometer or even bigger. These poor resolutions of the FTIR limitation always causing the scattering artifact on the sample from the spectroscopy. And if we want to use the ATR to make it higher resolution, but the ATR with the contact together with the sample surface always leading to the damaging of the sample. And once the sample being damaging, you will see there is a ineffective of the pressure mark there will causing the result become very confusing to the customer. Whereas for the Ramans, everybody know that Ramans have a biggest weakness is Raman always have a ubiquitous fluorescent baseline here. So a lot of the time we are confusing that this is the fluorescence baseline from the Ramans or actually from our sample. Because of the ubiquitous fluorescence baseline, then once we checking on the analysis, may causing the sample to facing the Raman lasers too long. And this will cause the laser damaging the sample. Once the Raman laser damaging the sample, it will leading to a unuseful spectroscopy data again because the data may not be accurate anymore due to the sample surface already being damaged. OPTR. What's so unique for OPTR from Micron? We're looking at the design of the OPTR, which is a mirage that we on. We know that we can see that there is a red infrareds. So this IR laser red is considered as a pump. They're pumping all the IR laser onto the sample surface. So what going to react with our interest of area will be the probe, which is a green color. So the IR is coming as a pump, but the reaction with our interest of the area will be the probe. So this probe actually is fixed design by the Mirage OPTR with 0.5 micrometer. As many people know that Raman's, the spot size or the spatial resolutions normally is 0.5 with 1 micrometer. So this OPTR with the design of 0.5 micrometer probe size, it will look like a Raman-like spatial resolution or spot size. So because of only 0.5, so it tends to be the point analysis rather than area analysis like acquired by FTIRs. So it will be definitely with the point analysis, it will tend to be the IR wavelength independent. Meaning that no matter which point you point on the analysis, the spectrum will not change. Whereas for the FTIR, because of the area is 20 micron or above, any moving of the area of the analysis, it may turn to changing the spectroscopy because the areas is turning to another area. So the third point, the interesting part for OPTR will be using the FTIR transmission light spectra in reflection mode. What does this mean for us? Meaning the photothermal actually react with the sample area of the interest, and they actually is absorb the IR. But what to bring this IR back to the detector actually is similar like a reflective move. So the transmissions, meaning for us understanding is the photothermal respond with the area of interest as a transmission line, meaning the absorption of the IR, and they bring the IR back to the detector as a reflection mode. So do the measurement of the spectroscopy. So it turned to be a transmission light because the absorption and reflector mode to the detector. Because of OPTR is a very independent with the size because only one spot size with 0.5 micrometer. No matter what sample size or sample shape you have, they will only analyze the area with 0.5 micrometer, which another word we also can mention as 500 nanometer. Is fixed. The number 4 interest for the OPTR is non-contact technique. As everybody know that FTR have a ATR attenuated attenuated reflective analysis. It always need to have a sample contact touching with the crystal in order to generate the spectroscopy. So OPTR, they did not have any contact with the sample surface. So no contact with the sample surface, it definitely will minimize it will eliminate the cross contamination. And because of the non-contact technique, it also can minimize the samples preparation. What it this mean? Meaning that sometimes if you contact the sample, it may already introduce some artifact or contamination onto the surface. So you may need to redo another time. Then you need to re-prepare the sample to remove the contamination and then continue to analyze by the ATR, FDR. Whereas this OPTR is non-contact, is definitely no matter how many times you analyze the sample, it will not have any like Raman burning mark or FTIR contact induced contamination and causing the sample need to re-prepare again. No more contamination, no more artifact contamination. So the last one is very interesting also. Like Raman, they have a autofluorescent impact. So this one OPTR will not like Raman impact by the autofluorescent. So because of they have a Raman light spot size, they don't affect by the autofluorescence, so it will be benefit for micron as well. Let's see the case study that we have after we have this tool. The first is enable the cross-section analysis. This is the sample that you should see in our failure analysis. So we have a subsurface delamination in our microelectronic specimen. So once this sample come in, we have in the failure analysis, we have two methods we can choose. First is either we pry open the sample and expose out the delamination area, or we do a mechanical cross-section to expose out the side view of the delamination. Both actually technique is reasonable in failure analysis. Pry open. So conventional FDR, because of the spot size limitations and also need a lot of sample preparation, so it definitely we need to have some sample prep. We pry open the delamination to expose out the defective areas for analysis. So the pry open have a limitations for the failure analysis, because once you pry open, you may have a chance already removing the top layer of the foreign material together. So the interest of the foreign material that causing the delamination may be already removed during you do the pry open sample prep. So but no matter how, conventional FDR have a very large area for the analysis, so we need to use the pry open method. So we pry open, we analyze this tuff, which is the die-attached front area, to see what is causing the delamination. So conventional FDR with the diamond cell analysis, we transfer onto a diamond cells and run with the transmission mode. We found is a polymer resin. But for OPTR, it is directly analysis. Directly analysis is, but the spot size is only 500 nanometer. So we need to do a few points to see whether how repeat is the data. So the data is repeatability, and we come out is a polymer resin and mixture and together with the chemical solvent. So both conventional FDR, we see polymer resin. OPTR, we also polymer resin. But the unique here for OPTR is, it seems for us, the OPTR is more sensitive than the conventional FDR, because they detected chemical solvent, which during we do the physical failure analysis, we use the chemical solvent to do the cleaning after we do the pry open. So OPTR sounds like very sensitive that they're able to the solvent that we use to do the cleaning before doing the IR analysis. So if we decide to go for the cross section, which is the desire, which is the more desire or keen interest by the failure analysis, because normally if we have the customer sample, the first thing they will do the mechanical cross section to see what is the defect mode of the units or the microelectronic specimen. So once they do the cross section, you see a dilemma for this kind of analysis. If we go to see use the conventional FTIRs, it normally will turn, even though we use the micro ATR with germanium crystal only 0.5 millimeter, it turn to be kind of too thin for the conventional FTIR to obtain a meaningful data, and it turned out with us is a noise spectrum. So in this kind of mechanical cross section with a very small area, it will always having a limitation for conventional FDR to do the analysis. So in the past, before we have the OPTR, this kind of mechanical cross section, if we want to do a organic analysis or organic analysis with IR spectroscopy, it is very, very hard or impossible to generate any spectrum. And mostly we are getting the noisy spectrum on it. Today, once we have the OPTIR with the 500 nanometer spot size and can be directly analyzed without non-contact on the sample surface, it gives you a very good result for the micron, and it changing something is very, very interesting to the failure analysis. So you see this is a mechanical cross section. OPTIR is 500 nanometers, so they need to do a few points. And once we do a few points, we average it out, and we manage to get out the very, very strong signal, which is a very real signal and not a noise signal. It's a very solid result. And once we go to compare with the database, it really come out with alkali raising and raising alkali emulsions. And this is very, very giving a good breakthrough for us, for micron, because we getting the delamination with the raising alkali or alkali raising, it actually have a linking that is a potentially is underfill material, because underfill material contain a raising emulsion inside. So this actually can giving a very, very strong finding for the failure analysis, that we know that this is the DAF, die-attached film, and we know that this is a substrate, die-attached film and a substrate dilemma. And why is a dilemma? Because the unintentionally, the underfill that's surrounding for the neighboring of the unique location is actually filling into this die-attached film and the substrate. And this is undesirable. It's not the desirable phenomena that we have should be. It's not the ideal part for the process side. So why this underfilling is the need will give a process need to understanding and investigate. But it really find out the root cause that underfill causing the delamination of the units or the microelectronic parts. Then another interesting part we can see from OPTR during we do this mechanical cross-section analysis. So like you see, there is also we do a left of the analysis, because just now is a right. So right now we do a left, and surprising that we see a spectrum is also a very solid, a real spectrum. Once we go and match with the database, it come out with a cotton fiber and cotton cloth. This is very, very interesting. Reason behind is during the mechanical cross section, the failure analysis team did use the cotton cloth to do the cleaning. Once they do the mechanical grinding, they need to use the cloth to do the wiping out the water or the stain that attach on the surface. So this kind of cotton and cloth actually is very traces amount, very low. So somewhat in the side views of the mechanical cross section, it able to detect by the OPTR, meaning that OPTR really is a very sensitive tool that actually can capture any material that present on the surface of the sample. And this is sometimes can give a very advantage for the analyst or the user of the tool, because the more information that you get, the closest of the failures or the closest of the root cause finding will be happen, meaning that you were very close to the root cause that causing the failure analysis. So this is a very impressed and interesting data that we have. Another advantage for this OPTR compared with the conventional FDR is definitely a particular analysis on the silicon die. As we have mentioned in the semiconductor, most of the time the particle on the integrating circuit, meaning the IC chip, is very small. It's almost 10 micrometer and sometimes can be less, smaller than 10 micrometer. So this particle always is the root cause causing the open circuit, delamination, the electronic part become overheating or some crack issue happen. In the past, once with the conventional FDR, this submicron 10 micrometer, especially 10 micrometer particle, is impossible to get any meaningful data. Most of the time, we only can get the noise signal because of the spot size limitations. So now, so you can see this FTR spectrum. We have this particle, and we analyze. We only can get, even though we use a transmission to transfer to a crystal, so that the background is only crystal, but we're still not able to generate any useful data, and mostly is artifact band. So this artifact band, actually sometimes if you go and do the further smooth of the spectrum, you may leading to think that is something of the material to match with the database. But now actually it really is a noise because of the you smooth the spectrum, you go to the wrong direction of the troubleshooting. So this is undesirable data that supposed to see. For OPTR, so let's see, you have these two particle. You can see there is a similar. If you see the physical or under the scope, they are look like same or almost similar. If you don't agree with the same, it's almost similar. So if you don't do any chemical analysis, you may think that these two particles is same. You may just as the same. So with the OPTR, with the small spot size right now is only 500 nanometer. You can see they actually have a two spectrum come out. And this one, if you really read the 1200 to 1000, which is this part, you can see actually it can point to a silica. It's a silica. So this particle is a silica. Whereas this particle, you see the spectrum, IR spectrum is very different with this one. So you know that definitely we know that it's a different functional, chemical functional group already. So it turned out to match with the database is a urethane. So two particles quite close to each other, the size, appearance similar, but chemically is different. So this is very useful because if you guess with the physical appearance, it may lead into a wrong direction also. So now come to my conclusion or my sharing. So first thing, definitely we'll know that the submicron special resolutions for the OPTR is not like a conventional FDR. Like just now, the conventional FDR, if we want to analyze the delaminations, we need to do a pry open to expose out the area of interest or area of the delamination so that we can do the IR analysis or spectroscopy analysis. Whereas for OPTIR, no matter you are doing a pry open to analyze, or you have a mechanical cross-section to analyze for the side view, it don't need any specific sample preparation. You can directly use the mechanical cross-section to do analyze, or you can directly use the pry open to do analyze. There is no say that I must do mechanical cross-section and I just can analyze, or I must do the pry open, I just can analyze. So it totally is a very good tool that you don't need to spend too much time for sample prep. So no tough decision because it's only one sample. Like just now I mentioned, if the customer want to find the defect mode by doing the cross-section first, no problem. OPTR can do after you do the mechanical cross-section or any cross or the FIB cross-section also can. You just cross-section, you do your defect analysis first, physical analysis first, electrical analysis first, and now you can go to do the OPTR. And OPTR is a non-destructive analysis. So it's no problem. They also can do the analysis very precisely. So I also want to highlight the sensitivity of the OPTR that we experience in micron. So just now you see a 2 data point. First, pry open. We do the pry open. The analyst actually did do the cleaning after the pry open with chemical solvent. OPTR detected the chemical solvent. Second, cross-section. They did use the cloth to do the wipe out of the water marks, or can consider doing the cleaning, some cleaning after the mechanical cross-section. But the residue of the fiber, very, very small one that left on the mechanical cross-section together with the foreign material, OPTR also can detect there is someone using the cloth to clean to wipe down the cross-section material, mechanical cross-section part. So it's really very sensitive. Anything that touching to the sample before, there's high chance OPTR can detect, can find out that what material is ever touched with this sample before. So it's very interesting. Second of the case study, we know there is no scattering artifact, meaning that what this means, the spot size is only 10 micrometer. If you use the conventional FDR, it definitely have a lot of scattering artifact spectroscopy happen. It's very, very noisy. And sometimes if the analyst or the scientist go and do the smoothing, it may come out with a misleading data because you thought that is a spectrum there, but actually is a scattering artifact spectroscopy. So whereas for OPTR with a small spot size and can be directly analyzed, no contact, it can identify the only 10 micron or even smaller. As long as they are bigger than 500 nanometer, you can know the chemical origin. You are very confident. You see just now the spectrum is very, very strong and real and solid. It did not sound like a scattering artifact spectroscopy. And it's very easy to do the database checking. That's all of my presentation. Thank you.
Thank you, Angeline, for that. I've actually learned quite a lot about industrial failure analysis as you guys have applied it. And not surprisingly, I'm actually getting quite a few questions coming in from our audience. So really, without further ado, I'll want to plow away at these. What is the maximum size of the sample that can fit into the tool?
I think it's 7 centimeter times 7 centimeter with the height of the 22 millimeter, if I'm not mistaken.
All right. That fits with what I know as well. Next one would be, if a sample could easily be damaged by the Raman laser, how could such a sample still be analyzed by OPTIR? Okay, so that usually happens when the sample is dark, or if you're using a green laser in Raman, so samples that are perhaps a little reddish, a little orange in color. Therefore, they absorb that light and heat up very quickly. So one way we overcome that for the OPTIR side is we can reduce the green probe power down to microwatts of levels, like tens of microwatts, at a point where Raman won't work anymore. But we can reduce it down to that level, and then we switch to a different detector. We switch to an APD, an avalanche photodiode detector, and that is an ultra-sensitive but ultra-low light level detector. So we then still get excellent signal noise in the infrared, so for OPTIR. At that point, any simultaneous Raman won't work because the Raman excitation powers are too low. But yes, samples that are typically damaged by Raman and where you have no other choice can be measured with OPTIR using this APD detector at tens of microwatts of power. Right, the next question, Engineer, I'll throw this for you. Can the OPTIR analyze small particles or contamination on metal substrates?
Yeah, definitely.
Okay, easy answer. The next question says, how does OPTIR give good infrared spectra even if the sample is rough? And so, Angelina, I'll take this one. And the answer for this is actually something that I talk a lot about, because one of the key points, and you've stressed it and I've stressed it, is the scatter-free, artifact-free aspects of it. And that's because with normal FTIR, you have different wavelengths. You have a very, very wide range of infrared wavelengths, and you're also detecting all of the infrared wavelengths, or measuring via the infrared wavelengths. And therefore, at each wavelength, they all scattered, all the particles will scatter differently. So different particle shape and size or surface roughness generate different scattering for every single part of the spectrum. And that gives you a huge amount of variability. But with OPTIR, we detect the signal through monochromatic light, so through a single wavelength green. And so there is no wavelength dependent scattering. It's constant, hence the spectrum isn't affected, as long as it's focused well, of course, it isn't affected by the roughness like a regular FTIR would be. That's my kind of long-winded but somewhat passionate answer, because I'm quite, feel strongly about this point. One of the finishing up questions will be, how are samples, and this one's for you, I think, Angelina, how are the samples typically prepared for making successful OPTIR measurements?
For OPTIR, we hardly will prepare the sample. And because we normally, the OPTIR just like directly use it, so the sample prep is almost, can say, no need, very, very little sample prep. Can say that almost no need.
Great answer, of course. And again, this will be the last question, I think. What is the smallest contamination that one can measure with this tool? In your experience, of course.
The smallest contamination that we experienced before is only 0.5. The smallest one is 0.5 to 1 micrometer.
Okay, excellent. Okay, and really with that, we are really pressed for time. So I want to thank you again, Angelina, for your time. It's always so great to hear. So you work with our instruments from really wide applications, from academic research to industrial failure analysis. I think it's fantastic. I also want to thank the audience, of course, for taking the time to dial in and listen to this webinar. I will let everybody know that the webinar is being recorded, so will be available for on-demand listening later. If you want to share it with your friends and colleagues, we will email you the link in the coming days. And for all those questions that we never got around to, of course, we'll answer those via email in the coming days as well. So everyone, thank you, and I'm wishing you a wonderful day.